Hello everyone. Now I am going to demonstrate my project on the title of liver cancer staging using random forest classifier. Liver cancer is one of the most deadly forms of cancer worldwide. It ranks among the top causes of the cancer-related deaths globally, primarily because it is often diagnosed at a very late stage when the treatment options are limited. Early detection and accurate staging of the liver cancer are crucial for improving the survival rates of the patients. Staging not only helps to assess how advanced the cancer is, but also guides doctors in deciding the best treatment approach. One of the most widely accepted staging systems is the Barcelona Clinic Liver Cancer Staging System. In this system, it's specifically designed to categorize patients based on the tumor size, liver function, physical condition, and other clinical factors, ensuring that each patient receives an appropriate and personalized treatment strategy. However, the random process of staging involves inputting complex CT scans and clinical reports, which can sometimes be subjective and time consuming. In this project, I have focused on developing a computer-aided diagnosis system aiming to classify CT images of liver lesions into their respective BCLC stages using a random forest classifier model. Here I have input an image showing BCLC staging and classification of the liver cancer. It has some 5 stages from the very early stage to the terminal stage. It has very early stage, intermediate stage, advanced stage, and terminal stage based on the nodule size. And also it says about the liver function, and it also says about the treatment for each stage. So this BCLG treatment and classification system is widely used for liver lesions identification and classification. So the main goal of the project is to develop a computer-aided diagnosis system that automatically classifies the liver into lesion images into the BCLC stages based on their features. And also to use image processing techniques to extract meaningful texture and shape features from the CT scans. And also to apply machine learning algorithms, particularly in the random forest classifier, to predict the stage of the liver cancer activity. So this work focuses not only on achieving high classification accuracy, but also making the feature extraction process interpretable so that the model's decision making can be easily understood. For this, I use data set which is used from this challenge. It is actually a liver segmentation challenge which was revealed as a part of the ISBA 2070 and MHCA 27 conferences. The key point about the data set is it contains 130 abdominal CT scans. The data set includes segmentation of the liver and tumor lesions, providing a clear overview of the affected areas. The images were sourced from multiple clinical sites, adding diversity and real-world variability to the data set. The data was downloaded from the CADL under the title Liver Tumor Segmentation Part 2. Each CT scan includes multiple slices from which we extracted individual 20 images, showing either a healthy liver sections or liver sections with visible tumors. And also it focuses on selecting representative slices that highlight the presence and characteristics of the liver tumors. So I have included some two sample images from the data set. A healthy liver stain with no visibility. And another one is a slice showing a reducing tumor in the liver. These images are processed to extract features that can differentiate between stages of the liver cancer. So in the data set, I have some 58,000 images, and the image size is of 256 by 256, and it is an RGB image. So in the I have training set and evaluation set with some balanced set in each class. So this is my project flow. where I have the input image, I have converted that city image to a relative image, and I have extracted the models, feature extracted models. So in these models, I have extracted two types of features. That is based on texture and shape. In texture, I have extracted mean, standard deviation, and the GLCM properties and average feature. In mean, it actually gives the average brightness value of across the lesson region. In the standard deviation intensity, it measures the amount of variation or dispersion of the pixel intensities. The GLCM properties, it actually gives the contrast and homogeneity value. And in average features, it is also derived from GLCM. The average feature capture complex textual features. And I use the average of all the 13 average features for each lesson image. In shape feature, I have extracted radius, area, and the linearity. In linearity, it measures the radius square divided by the area of the shed. So it helps us to understand if the tumor is more elongated or irregular. Higher linearity indicates less circular tubes, often in aggressive tumors. After extracting these features for each image, all the values were compiled into a structured data set, saved as a CSV file, which then used for training and enhancing the machine learning models. With the external feature data set, the next step was to train a classification model. I chose Random Forest Classifier for several reasons. It is very robust to overfitting, especially when dealing with the small assets. It can handle both categorical and continuous variables. It gives feature importance scores and helping us to understand which features contributed most to the predictions. And in training case, the dataset is being split into training set of 80% and test set of 20%. And I have used some label encoding to convert the BCL stages into numerical labels. The random forest was considered 100 trees and I fixed the random shade for invisibility. The model was trained on the training set and evaluated on the test set. After the model was built, the model performance was assessed. It was following metrics. That is accuracy, classification reward, and confusion matrix. In the random forest model, the accuracy actually was quite satisfactory considering the dataset size. A confusion matrix was plotted using a seaborne heat map, which clearly showed that early and intermediate stages have some overlaps, likely because their feature patterns are similar. Very advanced and late stage cancers were predicted with a relatively higher confidence. Additionally, I have trained a small neural network for comparison and plotted accuracy and log curves over training windows. So here, I have designed a pipeline to extract meaningful features from the university images. Using a random forest classifier, I was able to predict BCL series with good accuracy, and this method showcases the potential of machine learning in medical imaging to aid doctors in diagnosis and treatment. So let me go through about the code which I have used. So this is the code which I have used. So when you see how I have loaded the data, extracted the feature from the images, clustered them, classified them, and finally visualize the results. First, I start by importing all the libraries that we need. I used NumPy and Pandas for base data handling, CD2 for OpenCV, image processing class. Matplotlib and Seaborn, I have used these libraries for plotting graphs and visualizations. Then I have some specific libraries called the Sky Image and Matos for texture feature extraction. I also bring in image folder and transforms from PyTorch to load and transform images easily. For machine learning, I bring in clustering techniques and a random forest classifier modeling and the metrics include classification under record and the accuracy underscore score. Finally, for deep learning, I import Keras sequential model and this says. After which, I have loaded our training and values datasets. I have used the image folder from PyTorch Basically, image folder expects that our images are organized into folders by a class. But here, I use it just to quickly load images and apply a simple transformation, converting them into tensors using transforms block to tensor. We build the function of we build the number of the images in the training and evaluation folders just to confirm that our data is loading correctly. Next, I'm checking the image details. After loading, I defined a small helper function to check the image shape, how many channels are there, and what is the height and width of the image. I took one back from the data loader and printed its dimensions. This step is important because some models might expect fixed size inputs. I then checked how the classes are achieved in our data. Using counter function, it builds how many images are there per class. This is important because if one class has way more than images than the other, our model might get biased during training. Then, the next step is data extraction. We will go over all the images in the given data folder. For each image, we load it in a grayscale image because the grayscale is enough for our case because series scans primarily represent density values. I then calculated basic intensity features. Mean intensity, it actually calculates the average brightness variation and the standard deviation, how much variation is there, and also I have computed the texture features like contrast and homogeneity. In contrast, it measures the intensity differences, and in homogeneity, it measures the uniformity. I also extracted analytic features using Mahato SideWesh. Analytic features are advanced texture statistics that give deeper insight into the structural direction. Next, for tape feature, I first blurred the image using a Gaussian filter. This smooths out the noise. I applied a threshold to convert the image into a black and white format. I obtained the lesson boundaries and then found the contrast, especially the borders of the tumors. From the largest contour, I have extracted the area how big the lesion is and the radius is the smallest circle that can completely cover the tumor and some linearity, how elongated the tumor is. All these features for each image are collected into a list and finally I created a pandas data frame from them. The next process is cleaning clustering. I have grouped the images into 5 clusters because we have 5 stages in the DTH system. Stage 0, Stage A, Stage B, Stage C, and Stage D. Can use automatically group similar featured images together. I then manually map the cluster labels to the clinical stage names. Finally, I have saved all the extracted features along with their assigned stage into a CSV file named lesson underscore features underscore VCLC.CSV. Now that I have our feature data set, we move to our training and machine learning model, specifically the Random Forest Classifier. First, we import the stage labels like stage A or stage B into numerical labels using AMD and the encoder. And then we split data set into 80% for training and 20% for testing. And we make sure to stratify the split so that every stage is properly represented. We create and create a random forest with 100 trees. Random forests are great because they handle both large and small data sets. They manage both linear and non-linear relationships well. And they are resistant to overfitting. After training, we predict the labels for test step. And we calculate the accuracy score, the overall correctness of the model, and the classification review, showing the precision, recall, and reference score for each class. To better understand where the model is making mistakes, I have plotted a contribution matrix. It shows where axle and breaker labels match and where they don't. For example, if many stage B images are misclassified as stage C, we will clearly here. And then I will see the state map to map the confusion matrix visually clear. After trying the random forest, I also built an simple neural network. The architecture is the input layer, which has it is based on the number of feature. And the first neural layer, it consists of 32 neurons with the radio activation function. And the second neural layer with the 16 neurons, it also has radio activation function. And an output layer which has 5 neurons, but we have 5 stages with the softmax activation function. I have used the add optimizer and sparse calculated cross entropy loss. And also I have trained the network for 50 epochs, the batch size of 60. I also plot the training and validation accuracy and loss curves to observe learning progress. Finally, to make it all visual, I randomly picked some 30 images test set. For each series, I created the BCLC stage and also I have overlaid the triggered image onto the image using OpenCE's put text function. I also showed the actual stage for comparison. This gives a very intuitive sense of how good our evaluations are by seeing the real city images along with model outputs. So here you can see the outputs of the code that I have shown you above. The training images, it shows the number of training images and validation images. And the image size, the channels, it represents the RGB image at first. And after which I have using counter function, I have shown in each class how many images are present there in validation class and training class. And I have calculated the random forest classifier model accuracy. And I have printed out the classification report, which has precision, recall, F1 score, and support function. After which, I have plotted confusion matrix using Seaborn heat map. And for 50 epochs, I ran the model. Also, this is the plot of accuracy for the neural network that I have built. And this is the loss curve that I have got from the model. After which, this is the main step. This is the step where I have updated the model, whether it works good or not. I randomly pick some 30 images, and for each image, I have printed out the actual value and the weighted value. And for all most of the images, the actual weighted value matches. So this actually shows that we have extracted some meaningful features from the liberation images. And also we have clustered the immediate stages. And I have trained the random forest classifier. We also explore the simple neural network and we visualize how the model works on the unseen data. So this project showcases the powerful combination of image processing, feature engineering, and machine learning applied to some critical healthcare problem. So I have uploaded all my data set which I have shown in this video in my GitHub repository called computervision.git. You can get over there and you can see it and you can also refer it also. So thank you for watching this video.